Welcome to Mechanical Tutorial. I am going to teach you different techniques in SolidWorks for mechanical engineers. I am going to train you different modules like surface modeling, sheet metal and enclosure design, product design, plastic components design, reverse engineering and many more tips and tricks in SolidWorks. So before starting FEA analysis, we should understand basics about material properties and material types. So how do we select material? There are n number of materials in the market like steel, plastics, wood, cork, glass, ceramic, rubber, copper. How do we select different materials for different components? So for that we have to understand about some of the material properties, and this is about stress strain curve. So the linear slope is where the material doesn't deform at all. So there is a uniform thickness on the material cross section. So when it reaches tensile yield strength or simply yield strength, it starts deforming. So yield strength is nothing but maximum stress where a material start deforming permanently. That is called plastic deformation, and it is measured in Newton per meter square or pascals, or we can use PSI also. Next is ultimate tensile strength or simply ultimate strength or tensile strength. It is called UTS, where the necking of the component takes place. So tensile strength is maximum stress at which material start failing or breaking. So there is a slowly breaking of this component and finally it fractures. So usually we will consider where there is no plastic deformation. So the stress at which where there is no plastic deformation, that is tensile strength or tensile yield strength. So in material properties, when we apply material to any component, we have to consider at least 4 factors, that is elastic modulus. This elastic modulus is sometimes called Young's modulus, that is the slope of this stress strain curve. So this gives the rigidity or stretching or bending of the component. So how rigid is the component, it defines. Next, Poisson ratio I am going to explain in the next slide. Mass density. The density will gives us the idea about approximate weight of the component. So for same strength we can have different density, and that results in weight of the component. Sometimes weight of the component is very much important while designing aircrafts or automobiles. So this is very much important. Next property is yield strength. I have already explained. So the yield strength is maximum strength at which the material start deforming. So these 4 are important. So in Poisson ratio have the range of 0 to 0.5. So cork is having 0, glass is having 0.05 to 0.01, rubber is having 0.045 to 0.5. So rubber is having the maximum value 0.5. So if any value is near to 0 is brittle in nature, and any value which is near to 0.5 is elastic in nature. So it works like a rubber. So based on that, based on our application, we can select the material. So Poisson ratio is very much important while selecting the material. Sometimes we design very good product with good material, but suddenly it fractures because of brittleness. So Poisson ratio is very less for this component. So we have to be very much careful. So steel is having 0.27 to 0.3, aluminum is having 0.33, cast iron is 0.2 to 0.3. See, cast iron is very much near to glass, so it is brittle in nature. Some common metals is having 0.25 to 0.4, brass is having 0.33, copper is having 0.285. So let's see these different materials. Steel is having 0.27 to 0.3, plastics are having 0.3 to 0.36, 0.16 is having wood, and cork is having 0, glass is having 0.05 to 0.1, ceramic is 0.25. See, 0.25 is very much near to 0, so it is brittle in nature. Cork also is brittle in nature. Rubber is having 0.5, it is elastic in nature. And plastics and steel are lying between brittle material and elastic material. Now copper is having 0.285. So Poisson ratio plays a major role while selecting a material. So when we understand different components while doing the analysis, we'll get more idea on these material properties and selection of material. So let's go to the example. Hi, today I'm going to explain about FEA analysis of beam bracket. So I'm going to show you how to create mesh model and von Mises stresses and displacement. Before starting FEA analysis, we have to describe the problem statement. Beam bracket shown in the figure is fastened with steel beam on the ceiling of machine room using two M16 bolts. See, this is the beam. So it is fastened with two bolts, M16 bolts. The load of applied 1000 newtons on the inner cylinder surface. So here 1000 load is applied on this surface. The bracket material is aluminum 1060 alloy. See here, so aluminum alloy 1060 alloy. Find out the maximum stresses, its location in the bracket, and factor of safety. So we have to find these results. So this is the beam bracket dimensions. I have created a video on this beam bracket. You can check the link in the description. So beam bracket materials. So in material properties, the major properties we consider is for any FEA analysis: elastic modulus, Poisson ratio, mass density, and yield strength. So these are in megapascal units, and density is in kg per meter cube. So while generating any report, we have to write one discrimination. So I am going to share you this report, and you can check the link in the description. So boundary conditions. So what are the boundary conditions we are going to assume? Like the bolts are fixed at this hole locations. So those are fixed supports, and load is going to apply on the surface, that is 1000 newtons. So I am going to show you the results, and I am going to show you the what is factor of safety. So let's start the FEA analysis. See here, I have created this model in earlier video, so I am going to share you this PDF as well as the creation of this model video in the description. So before starting FEA analysis, we have to create a split surface because load is not completely applied on this location. See here. So it is applied at the bottom location of the cylindrical surface. So for that, what we have to do is we have to split the surface. So I am going to show you how to split the surface. So I have taken axis and selected this surface. Now I am going to create one plane. Select a plane. First reference this surface. Second reference this axis. So it is creating perpendicular. Make it parallel. See here, one plane has been created. Now you can stretch it as per requirement. Now go to split line. Select intersection. See here it is asking two options. One is split body, face or plane. I am selecting this plane and surface. I need to select this. So you can you can see these two yellow lines. These are split lines. Now this surface has been divided into two parts. Now hide this plane. Now let's start the simulation. So I am concerned about deformation and stresses. So create new study. In a new study, here we can apply the material. So it is taking as default because I have already applied on the component. So it is best practice to apply on the component itself. So it automatically takes the default material, or else we can apply from this edit material option. See here, this is aluminum alloy 1060 alloy. So these are the properties of the material. Now we have to apply the fixed geometry, that is fixtures. So how this bracket is going to fix on the beam. So wherever the bolts are clamped, so we have to apply the fixed supports. Say OK. Next go to the force. So apply force on this. See, it is showing radially, but load is applied in this downward direction. So for that, what we have to do is we have to select the direction. So automatically it asks for the face, edge or plane. So I am selecting the plane. Either I can select this plane or this face. Now it will ask for the units, how much load it's going to apply. See here, we can see the arrow direction. It is showing downward. Say OK. Now I have applied the boundary conditions. Now I am going to run the mesh. So before apply the mesh and run option, better practice is create a mesh, because if any error is there in the model, either at fillets or some locations, it will show error. Then we can modify the model instead of running this option, and it will minimize the system memory also. Create mesh, keep it default. So this mesh model is generated now. Now once again go to mesh option and select mesh and run. Now let's see the results. Stresses we can see here. So the maximum stresses are at this location where bolts are clamped. So these stresses can be avoided with some kind of fillets. So let's animate how the stresses are going to change. See here, we can reduce the speed. So how the material is behaving, stresses are developed here. So let's see the displacement. So maximum displacement is at this location. See here, rib is available and the other side is rib is not available here. So because of this reason, there is more displacement at this location. So in design optimization, we can add one more rib over here. That's how we analyze. So due to bolt clamping, here the blue color shows there is no displacement at all. So let's see the animation also, how it's behaving. See here. So it is moving in this direction. So it is around 1.066 mm displacement. So let's see the report. How do we generate this report? So based on our load conditions like fixed supports and load applied on this location, so these are the results obtained. Simulation results. Displacement is 0.017 and bond mass stress is 13.9 megapascals. So here 1.38 into 10 power 7 Newton per mm square I have converted into megapascals. So that is 13.9. So when we come to factor of safety, see the component material is 1060 alloy and deformation is 0.17 and tensile yield strength of this material is, as already mentioned earlier, see 27.5 megapascals and the stresses obtained is 13.9. So when we divide 27.5 divided by 13.9, that is yield strength by 1 mass stresses obtained, we get the factor of safety of 1.97, which is almost double the load applied. So it is some extent accepted. Further, if you want to improve the design, then you can change the material, or as I told you earlier, we can add a rebore here. That's how we optimize the design. So this is a brief about FEA analysis of beam bracket. Thank you very much.